So my lectures are going to be on sort of very elementary introduction to random matrix theory, and so the goal of this course is not to sort of tell you about the latest results in RMT or applications, but rather to sort of give you a basic introduction and familiarize you with the questions. What are the interesting questions? Why is it interesting? And also some basic techniques, so that if you read any paper in RMT, that you can sort of understand at least roughly what they're talking about. So in the first lecture, I'll just use the slides as well as the board, just to show you some pictures and so on. And the second lecture onward, I'll be totally on the blackboard. Okay. Is there any light here on the blackboard? Ah. No. This one? Last one. Okay. Yeah. Okay. So, okay. So random matrix theory. So historical. So this will be just a brief historical introduction to RMT, and so in the scientific literature, random matrix theory was first introduced by this gentleman called John Wishart. He was a statistician from Cambridge, and this was exactly 90 years back. This paper was published in Biometrica in 1928, and so his interest was the following. So as I said, he was a statistician. So the problem that he was interested in is the following, and this is the sort of first motivation of random matrix theory. So I'll just give you an example. So imagine that you have a class like us, okay, and let's say you have two subjects like physics and mathematics. In general, you can have many subjects, of course, and you have some students, number of students here, let's say 3. But in general, this is just an example. In general, it will be m students and n subjects. But let's say 1, 2, 3 students, and this x11, x12, etc. These are the, let's say, exam scores of the students. Okay, so the first student had score x11, x12, x21, x22, and x31, x32 is the third student. And so the question that he was interested in, oops, what happened? Okay, so question he was interested in, that is there any sort of underlying correlation between the physics and maths course, meaning that if somebody is good in physics, does that necessarily mean that she or he is good in maths, or vice versa? Okay, so we wanted to understand these correlations, and so how would you sort of progress? So he said, well, very obviously what you would do is, okay, you take this transpose of this matrix. So if it is a 3 by 2, transpose will be 2 by 3, and then you just take the product of the x transpose x, okay, and if you just do this simple exercise, you see that the diagonal elements are just the variance of physics course. Okay, imagine that this x11, this the mean has been subtracted, and you just divide by 3. Then this is just the variance of the physics course, right? And this guy here is the variance of the maths course. And off diagonal element here, so this is just the correlation between physics and maths, right? So this is the x11, x12 plus x21, this is the sample, correlation function between the physics and maths course. Okay, so this matrix, which is this product matrix, so this is called the covariance matrix. Okay, and this is unnormalized. And in general, this will be n by n matrix. Okay. So what does this covariance matrix tell us? So it tells us that it sort of encodes the information about correlations and fluctuations inside this matrix. And so if you look at the eigenvalues and eigenvectors of this matrix, then that will sort of give you some information about the correlations encoded in this particular sample. Okay. Now, how to sort of see that? So let's take a simple example. So imagine that, think of a situation where we are in a sort of, God has created a strange type of human beings such that there's perfect correlation between physics and maths. If somebody gets 1 in physics, gets 1 in maths. Somebody gets 2 in physics, gets 2 in maths. So in that case, so for instance, suppose that the scores are like this. Let's say physics. Okay, I know it from the back it might be difficult to see, but I'll try to write a little bit bigger. So imagine that you have exactly perfect correlation, you know. So I don't know, say -1 and 1. Okay. -1. So they get exactly same scores in physics and maths. Okay. So this is your score matrix. And so if you look at the covariance matrix, so the covariance matrix will be just 1 square plus 2 square plus 1 square. So that's, I don't know how much it is, 4 plus 2, 6. Okay, so this will be 6, 6, 6, and 6. Okay. So if we look at the eigenvalues, so the eigenvalue, there are two eigenvalues clearly. So there will be one eigenvalue which is 12, and the other eigenvalue which is 0. Okay. So this means that if you do a scatter plot, so let's say this is the physics course, and this is the maths course. So you have 3 students. So they are exactly on at point 1 here, then point 2, and point -1. Right. So there's a perfect correlation between this physics and maths course. And so what this eigenvalue is telling you that, so if you diagonalize this matrix, there will be 2 eigenvectors, which are just the rotation of this. So it says that in this direction, there is a large fluctuations, variance, which is the 12, whereas in this perpendicular direction, in the other eigenvector, there is no fluctuation, lambda 2 is 0. Okay. So they are always on a perfect line, and so this is a example of a perfect correlation. So if you do many samples like this, take many exams, and if you always find that they are always on a line, then you would say, okay, there is a perfect correlation between physics and maths course. Okay, and the signature of that is that one of the eigenvalue is very large, whereas all the other eigenvalues, let's say, 0. Okay, but of course, real world is never perfect correlation like that. So typically, if you plot this this physics versus maths course in a given sample, what you will find is some scatter plots like that. Okay. So what can I say by looking at this? How do I know what is the correlation? Okay. So so this was the question, and so in order to detect this correlation, what can I say about the correlations about just a random sample like that? So you need to compare it with something. Okay. So imagine now the opposite situation, which is the situation where it's perfect correlation, and imagine that there are absolutely no correlation. There is no correlation, totally. So imagine that these objects, these xi entries, they are completely random, independently random variables. Okay. So in that case, if you take this product, these are also will be random variables, and the eigenvalues and eigenvectors will also be random variables. So in that case, if you plot, just a random sample, you'll get some random points like that. Okay. So basically, the idea of Wishart was that you need to know the eigenvalue and eigenvector structure of a completely random matrix in order to compare with your sample. Okay. So this is, in some sense, completely random data. You can use that as what the statisticians call as a null model, right? Null model means that you want to compare with that. So if you see your, in your given data, if you see that it's more or less like the eigenvalue eigenvector structure are more or less that of a random matrix, then you will say, well, there is not much correlation between the points in the underlying data. But if it is very different from this, like this, then you will say, well, there is lot correlation. Okay. So what he suggested is, therefore, is that we should, as a null model, just as to build something to compare with, we should try to understand the structure, the eigenvalue and eigenvector structure of a completely random matrix. Okay. So this is the sort of main motivation of Wishart, that this is the used as a null model for random data in order to detect correlations under this in a given data. Okay, so and in fact, I mean, this is, even today this is very relevant even after 90 years, because this is the sort of heart. These are the heart of the data analysis. So, for example, I mean, if you look at the data from CERN and you want to sort of detect some signal like top quark, existence of top quark or something, or even this LIGO data for the gravitational waves, you have huge data, and so in order to detect correlations, so first thing what people do is what is called the principal component analysis. So some of you may be familiar with it. So this is the main tool for data analysis. It's called the PCA. So the PCA, the technique basically is that, so imagine that you have a situation where you have almost like this, lambda 1 equal to 12 and lambda 2 equal to 0. Then you will say that, okay, I mean, there is hardly any correlation, there is perfect correlation in that, there is no fluctuation in that direction. Lambda 2 is 0. So I can actually reduce my data. I mean, I don't need to know the math scores, because somehow I know that there is a perfect correlation. If somebody has, score 1 in physics, they will have score 1 in maths. So all I need to know is to, instead of this, full data, I need to just keep one column basically, because I know that there is a perfect correlation. So which means that basically I can throw away all the perpendicular directions. In general, there will be n eigenvectors, and I can keep only the largest one, and this is what is called the principal component. Okay. Now, whether you can apply in a given data, how, what is the sort of applicability of the principal component analysis, that's a sort of open problem. You don't know, given a data, how many eigenvalues you should throw away. How many you keep and how many you throw away. So that depends on, what your data is and how, and there is still a lot of ongoing research in statistics on that. But essentially, the, idea basically goes back to Wishart again, that somehow, you have to keep the principal components and throw away all the redundant data. And this is the sort of, and because you don't want to deal with a huge amount of data, you want to keep the sort of relevant correlations and, throw away all the other unnecessary data essentially. And so this is the dimension, it's called the dimensional reduction. And this is also again used in techniques like DMRG and other things, that somehow you throw away unnecessary data. And so random matrix is still very relevant today, even in the statistical data analysis for principal component analysis. And people use random matrix model to for example, to decide how many eigenvalues to keep and how many to throw away and things like that. Okay. Okay. So this is the sort of this beginning of random matrix theory, 90 years back. Yes. Right. So probably then if you take that value as the tangent or something, then you get this line. No, I mean, if you just when you diagonalize these things, right? So diagonalization means what? Means just a rotation of your data, right? So that's one eigenvector, and this is the other eigenvector perpendicular. Okay. So eigenvectors just give you the directions, relevant directions, basically. Okay. Okay. So this was in statistics, and then in physics literature, the random matrix theory was essentially introduced by Eugene Wigner. Now, if you ask a typical physicist, he'll tell you that, well, random matrix theory was introduced by Wigner. But the thing is that those days people are very honest. I mean, in fact, this was in a conference, and somebody asked him that, how did you think of random matrix theory in nuclear physics? So he said, then, as I mentioned, and this was known a long time ago by Wishart. So he actually knew about Wishart's work. And in fact, at the end of this conference, so somebody asks him that where does one find about a Wishart distribution? So Wigner replies, Wishart distribution is given in S.S. Wilkes' book about statistics, and I found it just by accident. Okay, so accidents happen, and this was a good accident. So so he actually knew about Wishart's work. And so he got the main idea about the RMT, and then he used in nuclear physics. And so what was Wigner's contribution in nuclear physics? So let me just tell you this. So oops. Okay, so nuclear physics. So essentially, imagine that you have, some heavy nuclei like uranium-238, atomic number 238, or thorium, atomic number 232. So experimentalists can give you the spectra. Okay, so these are the energy eigenvalues of these atoms. Okay, and this is a schematic picture. So it just gives you the this energy eigenvalues, and so if you look at these, and then they ask the theorists to explain these eigenvalues, okay? But if you think that in order to get the eigenvalues, what you have to do, you have to take your many-body system, which is this atom here, schematically. So there are protons and neutrons, and there is a sort of complicated many-body Hamiltonian, and you have to solve the Schrodinger equation of this Hamiltonian to get the eigenvalues. Okay. The problem is that you don't even know what the Hamiltonian is, okay? So this is a very complicated interaction between them, many body objects, so it's very hard to start from first principle and get this exact location of the eigenvalues, okay? So, but then, the point is that, okay, why would you want to do that, okay? People have developed all kinds of techniques, approximate techniques to get the eigenvalues, but maybe that's not what is very interesting. So what Wigner sort of noticed is that even though the exact locations of the eigenvalues are different in the two atoms, but you see from this picture roughly there is some kind of statistical self-similarity. Okay, so what that means precisely, so what he asked the experimentalist to plot the distribution of the spacing between eigenvalues. Okay, so you take your spectrum like that, and you just look at the energy difference between nearest neighbor eigenvalues. Okay, and so let's call that S, and you just draw the histogram of S. Okay. So if you do it for uranium, you will find some graph like that, and if you do it for thorium, then you will find something like that. Okay, so what's the big deal? But then, what he realized is that, okay, I mean, there is, you have to scale it. So usually, so there is a mean spacing between the energy eigenvalues. So what happens is that this is, so let's say the mean spacing is S bar, which of course varies from uranium to thorium, and this is a scaling function which is normalized to 1, and it's some function, let's call it small p, of S over S bar. Okay, so if you plot, instead of PS versus S, if you plot S by S bar and multiply this guy by S bar, then these two curves fall on top of each other. So that's what scaling means, they collapse onto each other. Okay, and so this was the first thing, that indeed, experimentally data, I mean, if you look at this, they fall exactly on top of each other. Okay, and so then he said, well, I mean, if it is like this, I mean, you don't really, it will be stupid to really, try to solve Schrodinger equation and find, these things. If it is universal, there must be some other physics behind it. Okay, there must be some other way to get this curve, rather than trying to solve Schrodinger equation of a complicated Hamiltonian approximately. Okay. So then Wigner came up with this idea that, well, the Hamiltonian, which means that in some basis it's a matrix, right? So your Hamiltonian, if you look at in some basis, it will be just a matrix with some elements Hij, and it has some symmetry. For example, I mean, it can be complex Hermitian or it can be real symmetric, so that the eigenvalues are real. And what he said is that, okay, I mean, so first approximation, what you can do is that to say that the system is sufficiently complex, so we can just replace this Hamiltonian by a completely random matrix, which means that there is in the entries of this matrix, So this is a real symmetric matrix, so you need to just look at the upper half. These things, lower half is automatically decided by symmetry. And you take these elements to be completely random Gaussian elements, okay, and see what it gives, okay, and then calculate the spacing distribution. And the chances are that it might actually, you know, tally quite well with this. And indeed, Wigner couldn't calculate this for n by n matrix. So what he did is just a 2 by 2 real symmetric matrix. So you just take a 2 by 2 matrix, x11, x12, and x12. It's a real symmetric matrix, let's say, x22. This is your Hamiltonian, basically. Imagine. And you just, you know, calculate, and you assume that this, you know, these guys are just independent Gaussian variables, okay? And you calculate the 2 eigenvalues. So they're also random variables. And from that, you calculate the, you know, distribution of lambda 2 minus lambda 1. Okay? This is the spacing. Just a 2 by 2 matrix. So there's only one random variable s, and you can compute its spacing. And in fact, in the scaled units, you find that this scaling function was okay, up to some constant. I don't write down this constant exactly, but something like this. Okay? So this is easy to, we'll see that later. This is easy to calculate for 2 by 2 matrix. Okay, and now if you, so then Wigner asked the experimentalists that, okay, I mean, can you match your data with this curve, okay, with some proper constant here? And indeed, you know, this curve described this very well. Okay, so this is what is called the Wigner surmise. So now people know how to calculate the spacing distribution for n by n matrices. Okay, this was just a 2 by 2, and it's a much more complicated form, and it's written in terms of what is called a Fredholm determinant. I'll explain that later. And but you know, if you actually see the n dependence is very weak. So 2 by 2 result is already, you know, once you properly scale these things, 2 by 2 result was already pretty good actually. Okay, so if you do by n, you know, it just changes very little, you know, from this. So n dependence is extremely weak. Okay, so therefore Wigner's surmise was already, you know, pretty good, and this was a big, you know, sort of success in nuclear physics. And you know, this was in fact this conference. Yeah, this was this curve there, px versus x, and probability of Levin spacing. And so this was how basically it came to physics literature, the nuclear physics literature, that that somehow, and the main doctrine of Wigner was precisely that if you have a sufficiently complex system, somehow it becomes simpler. Okay, you should be able to, you know, describe it with a much simpler description, which is totally random. Okay, and that's a much better approach rather than the first principle approach of solving by Schrodinger equation and complicated Hamiltonian. Okay, so this was the sort of main idea of RMT in nuclear physics. And then, you know, in the 50s and 60s, you know, the theory of random matrices was developed, you know, much more, which I'll talk about, you know, by Dyson, Godin, Mehta, and many other people. And but the main point which I want to say is that, you know, this basic doctrine, this is Wigner's doctrine, I'll call it. So what is Wigner's doctrine? Is the basic idea came from this, that, you know, if you have a system, we'll see some examples. If you have a system where, you know, which allows you to have some kind of matrix description, okay, we'll see some examples of that. And you know, if the system is sufficiently complex, you don't know much about the system, then the first thing to try is try a random matrix, but keeping the basic symmetry of this Hamiltonian. You first figure out what are the symmetries, and then, you know, you choose your matrix elements randomly so that it satisfies this basic symmetry. And then chances are that, you know, this description might be a very good approximation to your actual system. Okay, and it's not just nuclear physics. I mean, it goes much beyond nuclear physics. Any system which has some kind of matrix description, this Wigner's doctrine might be very useful. Okay, and this was indeed the case, as you see from, I've just listed some of the applications of random matrix. So I started with nuclear physics, and then, you know, quantum chaos, Disorder localization, you will hear some of these stories here from the talk of Marcus Muller and other people. And mesoscopic transport, quantum entanglement, gauge theory, QCD, matrix models, string theory, statistical physics, growth models, interface directed polymers that Herbert Swan is going to talk about. And also more recently in cold atoms, which I'll talk in some more detail later. And then in mathematics, Riemann zeta function, which again Giuseppe is going to give you a talk on that on the 13th of February. And so I'll just mention a little bit about that. So I'll just just to show you, and you can and then it goes on statistics, information theory, economics and finance. And there's a very nice book by Garno Takeman, Jinho Baik and Philippe Di Francisco, which has a collection of many of the modern applications of random matrix theory. Okay. So just to give you a few other examples. So let's take this quantum chaos. So this was very fashionable in the 80s and 90s, and it has become fashionable again now in the context of many body localization that Marcus is going to talk about. And so what is quantum chaos? So you all know about what is classical chaos. So let me just remind you. So classical chaos means that, okay, imagine that you have a box like a rectangle, and you just take a particle, and this will give some initial velocity, and so this guy will just move and get reflected from this wall. It will move like that, get reflected again, just moving by Newton's law, and so on. Okay, so let's call this trajectory 1. And now if I take another particle, which I'll call 2, and I start from very close to initial point to this particle, and I observe this trajectory. So there's only slight difference in the initial condition. Okay, and the idea of chaos is that if these two trajectories stay close together, then you will call the system as regular. Okay, and chaotic means that somehow the distance between them will diverge exponentially. So that means if you look at, for example, just the distance between the two trajectories, x1t minus x2t, and you take the norm of that, then this will increase exponentially with some lambda. This lambda is called the Lyapunov exponent. So if lambda is positive, then we'll call the system as chaotic, meaning that the two trajectories, slight difference in initial condition will exponentially diverge with time. Okay, whereas in the regular system, this lambda is less than equal to 0. That means they stay together. Okay. So this is the sort of classical definition of chaos. Now, what is the quantum problem? So how do we say, so in this particular, for example, if I take this particular rectangular trajectory, you will find that classically this is regular, okay? But if I just round the corner, okay, just make it a billiard. So just round these four corners. So this is called the billiard. It's like a billiard table. Here if you look at again two trajectories, they start very close, but then they exponentially diverge. Okay. So this is chaotic. Whereas in a perfect rectangle, this is a regular system. Okay. Now I want to do quantum mechanically. So what does it mean, quantum mechanics here? So quantum mechanics means that I want to again take a single particle. I want to solve the Schrodinger equation for this single particle inside this geometry. And look at the energy eigenvalues, the spectrum. Okay? and with the boundary condition, that absorbing boundary condition, so psi is 0 on the boundary. So if you do it for the rectangle, we all know how to solve this Schrodinger equation, and you will find some spectrum, okay, which looks like this. So these are points basically on a line, okay, the energy eigenvalues, and so this is the rectangle. And if you do it for the billiard, you have to do it numerically. Billiard, you cannot solve it exactly. And so you will again get some points here. So the question was that, I mean, how do I distinguish quantum mechanically whether a system is regular or chaotic? Classically, I know this is my definition, that I look at the trajectories and whether they diverge or not. Quantum mechanically, there is no notion of trajectory. So how do I, only thing that I have at my disposal is the energy spectrum, okay? And by looking at the energy spectrum, can I say something whether the system is regular or chaotic, okay? So looking at the spectrum, regular or chaotic. So what is the signature of chaos basically in the spectrum? That's the question. Okay. And so what happens here, again I won't go into the details, this is just an overview talk. So what happens here is that if you look at the rectangular things, you have these points, and these points behave almost like a Poisson distributed point. So imagine that you just throw some points at random, okay, on a line with some mean spacing between them, and then if you generate this Schrodinger equation, you generate the eigenvalues, they behave almost similarly. So this is here. So that means, what that means is that the spacing distribution here will be roughly exponential distribution with some constant here. Okay. If I draw the histogram of this. Whereas in billiard, if you do that, and this is what people did numerically, and what they found is that here, in contrast, it actually behaves like, something like that. Okay? So this is exactly like the Wigner surmise things. So, sorry, S square. Okay. So in some sense, so the points, the energy spectrum of the billiard sort of behaves like almost like a random matrix eigenvalues, okay? And then this was the sort of the conjecture. So this goes by the name of BGS conjecture. So this is Bohigas, Giannoni, and Smith. It's about 84 or something. So the BGS conjecture says that basically, any system which is classically chaotic, if you quantize it, that means you solve the Schrodinger equation, find the spectrum, then once you rescale properly, you will always see random matrix spacing distribution. So they behave, these eigenvalues, they behave as if like like that of a random matrix eigenvalues. Whereas if you take a regular system, and this is this conjecture called Berry's conjecture. So Berry's conjecture says that if you take a system which is sort of integrable, like for example the rectangle and regular system which is classically regular, if you quantize it and look at the spectrum, then this will be always kind of Poisson structure exponential distribution. Yes. Yes.
The length of this rectangle, somehow the ratio is irrational.
Yeah, I mean, so these are details. I'm not getting into the details of this, but basically, if you do it, and if you take very high energy part of the spectrum and just draw the histogram, you will basically essentially still see. So the two graphs will look like this. So in one case it will be exponentially decaying. I'm plotting this PS versus S, and the other case it will be like that. Okay. This, by the way, is the logo of our laboratory. It's called LPTMS. And well, Boigas was, he was one of the founding members of our laboratory. So, so this is the sort of logo of our lab. Okay. So, anyway, so I mean, I'm not getting into the details because this will take me ages. So this is the sort of so another application of somehow that in a chaotic system the eigenvalues they behave like the eigenvalues of a random matrix. Okay. And the last, I mean, maybe one other example I'll talk before I move. Let me take. Okay, I'm not going to talk about growth models and interface. That Herbert will talk in detail later. And so what I'll here just mention briefly the zeta function. So Riemann zeta function. Again, I mean, without going into details, again, Giuseppe is going to give a talk on Riemann hypothesis. So you will hear all about it. So Riemann zeta function is defined for, okay, so all of you know this is 1 over n to the power z, n goes from 1 to infinity. And this is a convergent series for z bigger than 1 in the complex z plane. And you can define in the whole complex plane by analytic continuation of this function. Okay. So full complex z plane. So this is the zeta function. And the famous, okay, so zeta function has many zeros in the complex plane. Okay. So zeros means that you want to look at the values of z such that this is 0. And so there are some trivial zeros. So trivial zeros is just basically when this z is minus 2m, where m equal to 1, 2, 3, etc. So these are on the real line. So you have at minus 2, minus 4, minus 6, etc. These are trivial zeros. And there are some non-trivial zeros. Which are supposed to be on this imaginary line with real part half. Okay. And they are on this line. This is the famous Riemann hypothesis. Well, so if you can prove this, you will get $1 million from the Clay Foundation. This is one of the most famous open problem in mathematics in number theory. And so there are people still who try to prove Riemann hypothesis, and it's obviously very sort of deep problem. But then people actually tried. Okay, I mean many different avenues to solve this to prove Riemann hypothesis. But one of the things that people tried, they said, okay, I mean imagine that Riemann hypothesis is true. Okay, so then you have all these non-trivial zeros lying on this imaginary line, and then you can actually ask, what is the spacing distribution between these zeros along the imaginary axis? Okay, and so there was this famous mathematician called Andrew Odlyzko. He was in Bell Labs, and so he built special computers to study these zeros of this Riemann zeta function, and people have found billions of zeros now, and there have not been any exception that they are outside this line. So numerically, you see that all of them are on this imaginary axis, and so Odlyzko had data for billions of zeros on this line, and then he just plotted the histogram of the spacing distribution. Okay. At a sort of high energy level, and in fact again in scaled units, this s is again the distance between the zeros along the imaginary axis. So what he found is that this behaves like, now this is the spacing distribution for complex Hermitian matrix, random matrix. Okay, we'll see that later. And so again, sort of as if these zeros behave like the eigenvalues of a complex Hermitian matrix, let's say. Okay, so this was sort of and then people like many people like Keating, John Keating, and Smythe, Montgomery. So these are all sort of Montgomery. So they studied many properties of these detailed properties. For example, the correlation functions between these zeros and the other objects, number of zeros in a given interval, and so on. And they compared with the prediction from random matrix theory of a complex Hermitian matrix, and it matches beautifully. I mean, so there is obviously a deep connection between the zeros of the zeta function and that of the complex Hermitian random matrix. Although what is the precise connection, we still do not know. But I mean, all the properties that you could calculate on these things and compare with random matrix, it seems to hold. Okay, but okay, this still there is no proof yet. Okay, rigorously mathematical proof. Okay, so okay, so you see that there are many examples where somehow the random matrix theory appears as a sort of natural way in spacing distributions, and then as I go along, I'll talk about many other interesting problems like the determinantal point process and so on. And so what I'll do now is okay. So this is the sort of beginning of my introduction to this subject. And what I'll do in these things that the more recent application is what is called the cold atoms. Okay, and you will again hear from Andrea's talk, I suppose, or somebody else's talk from cold atoms. So I'll just tell you briefly what is the sort of connection between cold atoms. Not tell you the connection, but which I'll develop, but I'll use the language of cold atoms. Okay. So what is cold atoms? So you know that these days there have been amazing experimental progress in the study of cold atoms, and which actually allows us to understand sort of the interplay between the quantum and thermal fluctuations of many body systems at low temperatures. And what happens in these systems is that you can have interesting quantum many body effects even in absence of interactions. Okay, for instance, we know that for bosons you can have Bose-Einstein condensation, even though there is no direct interaction between bosons. Many bosons can sort of compile into the ground state, and this is called the Bose-Einstein condensation. And similarly, for the fermions, the Pauli exclusion principle, which tells us that two fermions cannot be in the same state. Okay, so even though there is no direct interaction between the fermions, non-interacting free fermions, but still you can have very rich quantum many-body physics just because of Pauli exclusion principle. And we'll see later that these eigenvalues of a random matrix and the fermions of free fermions in a harmonic trap, they actually are exactly identical to each other. And so in a typical experiment, in the experimental situation, what you generally trap these atoms in a laser trap. You create a laser trap by optical lasers, and so they are confined in space, these atoms, and typically it's a harmonic trap, although they can design other types of potentials also, and they can do it in not just 1D, but not just in 3D, but 1D, 2D, 3D, and so they can tune also the interactions. They can do all kinds of things basically these days. Okay, but the typical setting is that there's a trap, and these atoms are confined in some limited region of space. Okay, and imagine that these are just free fermions. Okay, now if you look very close to the trap center here, okay, so you don't feel the trap, right? You don't feel the curvature of the trap, so you almost feel on the on the scale of the interparticle distance near the center of the trap, you feel that the system is almost translational invariant because you don't see the curvature. Okay, so in that case, so this is what I call the bulk. Okay, so in that case you can understand the behavior of this system in those regions near the trap center by the traditional many-body, free fermion physics that you'll find in any standard textbook. Okay, just a free fermions, basically Fermi liquid theory or something. Okay, so this part is very well understood. Okay, now what happens is in presence of a trap that when you go away from the bulk center, then you see that they cannot go very far away because of the trap, right? So they are confined in a space. So they will at some point they will end. Okay, if you look at these atoms near the edge, so there are these edges symmetrically in this particular example, and so it's here the fluctuations are very dominant, of course, because there are few atoms here. So there are fluctuations play a very important role, and you cannot apply the traditional many-body which holds for translational invariant system all the way up to here. So you need to find some new techniques to understand the edge physics in these cold fermion systems. Okay, and it turns out that there are some universal edge properties, which is universal in the sense it does not depend on the details of the potential, and that their behavior is extremely well described by, again, the eigenvalues of a random matrix. Okay, so when I develop some of the basic techniques of RMT, this will be complex Hermitian matrix. So I'll actually use this language of quantum mechanics because most of you are physicists, so you are familiar with basic quantum mechanics language. So when random matrix theory, when mathematicians describe, they use different techniques. Same technique but with a different name is called the orthogonal polynomial, which is just quantum mechanics essentially. So, but it's easier to somehow understand for us to use the quantum mechanics language. So I'll develop using this quantum mechanical language and to understand the bulk and the edge properties of the free fermions. And basically this will be isomorphic. This will behave, the positions of the fermions in a trap in 1D at 0 temperature will behave exactly like the eigenvalues of a complex Hermitian matrix. Okay, so this is what we will see. And this is just to show you a picture, because these days, people can't really, take pictures of the atoms. So this is the fermions in 2 dimension. This is from the Greiner group in MIT, and 2 dimension in a harmonic trap, and you see that again there is a sort of edge roughly, and you see a lot of fluctuations near the edge, and this is the sort of bulk in the center. Is roughly circular things, and so you can actually experimentally probe the fluctuations of these atomic positions. Just take a picture. It's called the quantum gas microscope now. Okay, so this is the sort of program that I'll develop. So should we take a break now and then restart? Okay, maybe you. Okay, so all right, so. Okay, so after this, initial introduction, which is a little bit, I didn't go into the too much details, just to give you an overview of the applications of RMT and why this is interesting and why is it still very useful, because more and more newer and newer applications which come about, and somehow the Wigner's doctrine is still very useful one. And so now I'll just go into precisely defining what I mean by random matrix and some basic tools that we need. So we'll talk about mostly I'll focus on random matrices with real spectrum. Okay, and so I have a matrix X which is Xij, and this is a n by n matrix. Now, in general, I mean, if you don't impose any symmetry, if you diagonalize this matrix, you will get n eigenvalues, which are generically these are complex, right? Because if you don't impose any symmetry, okay. And people have been studying complex eigenvalues of random matrices quite extensively, but we'll focus mostly on eigenvalues that are real. Because again, you can think of this X as your Hamiltonian of some complex system, and so in that case, you'll always have real eigenvalues. And so there are three types of matrices which have real eigenvalues. So these are called Dyson's threefold way. So all of you know that if you have a real symmetric matrix, which means that Xij equal to Xji, or X transpose is X. So this has real eigenvalues. We also know that there is complex Hermitian, which means that these are complex numbers, and Xij, okay, maybe X dagger is same as X. So Xij star is Xji. Okay. And then there's a third one, which nobody usually talks about, and this is called the complex quaternion. So quaternions are just generalizations of complex numbers with base 4, but again, I mean, these are some applications, but I'm not going to the details because it will take some long time basically if I want to develop this. Okay, you can look up Wikipedia if you are interested. Okay, so okay, so all these three types of matrices, they will have real spectrum, and these are called Dyson's threefold way. So Dyson was interested in the classification of random matrices with real spectrum. So he proved that there are these three types of matrices, which gives rise to real spectrum. Okay. Okay. So this is just so now I've not talked about the random matrix yet, and so now the generic problem is that you have this matrix. So let's say real symmetric matrix. Okay. So let's focus on real symmetric for the moment. Okay, so you have this matrix, and so somehow you want to assign. So let's think of this 2 by 2 matrix, okay? Because it's easier to write on the blackboard, so I'll just use 2 by 2. In general, in your mind, you can do it n by n generalization trivially. So here, because it's a symmetry, so all I need to specify is just the three elements, entries, x11, x12, x22. And so somehow the idea is that, okay, the whole problem of random matrix theory is that you want to assign some statistical distribution to these degrees of freedom. Okay. And so you give me this joint distribution of the entries, okay, and then you can generalize. Okay, in general this will be whatever n into n plus 1 over 2 elements. So you give me this this joint distribution of entries, and then for each realization of this matrix, I can diagonalize this matrix, and this diagonal matrix will be, in this case, 2 by 2. In general, there will be n eigenvalues. Okay. So clearly, these eigenvalues are also random variables, right? Because they will fluctuate from sample to sample. So each time I generate my matrix from this distribution, I diagonalize, I get eigenvalues. So you'll have these eigenvalues will, so lambda 1, lambda, there will be in general n eigenvalues. And they will fluctuate from sample to sample. And the whole name of the game in RMT is to understand, so these spectral statistics of these eigenvalues. Now this is in general, so basically the main problem that you have is that, if I give you the joint distribution of the entries, you want to somehow calculate the joint distribution of the eigenvalues. I use the same P just, as a probability, but it's not the exactly same P as this, okay? So question is that given this, distribution of the entries, product, okay, this object basically, okay? So given this, how can I calculate this joint probability density of the eigenvalues? Okay, so this is the central problem in RMT, and it's a difficult problem. You cannot do it in general. Okay, and so when you specify what is our distribution of the entries, so this is what is called the ensembles of random matrices, and we'll see that there are certain classes of ensembles for which you can actually calculate the joint distribution of eigenvalues exactly, but there are classes for which you cannot. Okay, and these are still hard problem. Okay, so now before even I assign what is the probability distribution of these things, I just remind you, just a few basic properties of matrices that most of you are familiar with, but so again, unless otherwise mentioned, I'm just, I'll just think of real symmetric matrix, but the generalizations are sort of straightforward. Okay, so first remark is that if you have, a real symmetric matrix like X, and if I make an orthogonal transformation or similarity transformation, okay, which I'll, just denote it by this, is in general I use this dagger for transpose basically, the real symmetric matrix. So I make a orthogonal transformation of this matrix and I arrive at a new matrix Y. So Y is also n by n, and in fact it's trivial to see that Y dagger is also Y. So Y is also a real symmetric matrix. And moreover, that the eigenvalues of Y is the same as the eigenvalues of X. This is trivial to prove. I mean, this is, basically when you just, we just rotate. So, I will not prove it, but this is a home, task basically, that home task, if you like. So this is very easy to show that the eigenvalues of Y are the same as eigenvalues of X. Okay. So when you make a similarity transformation or change of coordinates, basis, essentially eigenvalues don't change, but the eigenvectors will change. Okay. So eigenvectors okay. And the proof is very simple, because if you take this matrix X and you take a particular eigenvector like that, but the X is just S Y S transpose. Okay, so you write S Y S transpose operating on lambda gives you lambda. You just replace S by this, and now if I make S, remember that S is a similarity transformation, so this is identity. So if I now operate S dagger on both sides, so this gives you Y S dagger lambda, because I'm just multiplying by S dagger and using this as an identity matrix. So Y S dagger lambda is same as lambda S dagger lambda. So you see immediately that this guy here, S dagger lambda, is an eigenvector of Y, but the eigenvalues are exactly same, lambda. Okay. So and similarly you can reverse it and show that all the eigenvalues of X are same as eigenvalues of Y, and but the eigenvectors are different because they are rotated by this S dagger. Okay, so this is a trivial remark. A little less trivial remark is so again think of this 2 by 2 matrix. Now before I assign a weight, I want to look at the volume element. So in this case my independent degrees of freedom are just these 3 elements, right? So look at the volume element dx1 dx1 to dx22, right? This is my whatever weight I'm going to assign. This is my volume element for that. Okay. So think of it's like a uniform distribution. Okay. So now, if I rotate this matrix, if I make a similarity transformation to this X and go to Y, okay. So as I said, Y is also going to be real symmetric matrix. So volume element of Y is going to be this. So there is a Jacobian involved, okay? But the statement is that this, for any similarity transformation, this is exactly same as so Jacobian is 1. Okay? So no matter you just make a similarity transformation, the volume element is invariant under this similarity transformation. Okay? So there is a fancy name for it, this theorem, which is called the Haar measure. Haar measure means uniform measure. So Haar measure is invariant under similarity transformation. This is not a completely trivial statement because it's not the full matrix X here, because you have only these 3, not all of them. And to show this, so let me just demonstrate this for 2 by 2 so that you have a sort of idea, and then I'll leave as an exercise the proof for the n by n. Okay. So the 2 by 2. Oops. So, so I want to make an orthogonal transformation. Now 2 by 2 matrix, you know very well that any orthogonal matrix X, so S transpose S should be identity, and it's 2 by 2. So I can always represent it, parameterize it by a rotation matrix, which is cosine theta, sine theta, minus sine theta, cosine theta, right? So theta just tells you how much it rotates. So if I now look at this Y, which is, okay, maybe this is minus, doesn't matter, okay. So then the Y, which is S transpose X, so Y is this. This is not the most elegant proof, but this is a direct, hard proof demonstration, which I find quite nice to see. Okay, so this is your transformation, right? This is exactly this guy. Okay, parameterized by this theta, and so you can write down the elements of Y. So Y11 will be just x11 cosine square theta plus x22 sine square theta. Just multiply it out And finally, the last one, which is okay. So just multiplying out this. Okay, and then you want to calculate this Jacobian, right? Because the statement is that if I look at this volume element after the similarity transformation, yes, 2, 2, 1, 2. So this will be this Jacobian times dx11, dx22, dx12, and we want to prove that the determinant of this Jacobian is 1. Okay. So what is this Jacobian matrix then? So again, I am doing it in great detail just to demonstrate you that how it comes about, etc., etc. Okay. So given this relation here, so you can immediately compute this matrix. So this will be cosine square sine square 2 cos theta sine theta sine square theta cosine square theta minus 2 cosine theta sine theta, and so this is your Jacobian matrix, and then you can just compute the determinant of that. It's quite trivial. You can just add the row and column, etc., and determinant of J. So if you evaluate this, you can use Mathematica if you want, but I just did it by hand, and it's this 1. So, so this is the statement, right? So now the exercise prove that this determinant of J is 1 for n by n matrices. Okay. It's not too difficult. You just have to think a little bit. But if you don't find it, then I'll do it. But okay. But this is a sort of important fact that we'll have to use later. That again just under similarity transformation, the volume element don't change. Okay. Just that's the statement. Okay. So. All right, so yes. Yes. Absolutely. That's right. Yeah, exactly. Yeah. All right, so now, going back to this, so we want to, again think of this, always this 2 by 2 matrix as a sort of reference. And we want to, you want to now 2 by 2 and general n by n. So I want to now, choose all these independent elements, dx1, dx1, 2, dx2, 2 for 2 by 2, whatever. This whole thing I'll generally denote by this d of x. Okay, and you know that the d of x does not change under similarity transformation. Okay. So now we have to choose somehow this p, and so that will specify my random matrix. Okay. Now there are two categories of matrices that people mostly study. So the first one is generally called Wigner matrices. Which says that, these elements, they're just independent. Okay, you choose each guy independently. Okay, so for instance, in this case, I can choose my p of x11, x12, x22. Some function, let's say f1 of x11, some normalizable function, some function, some other function, maybe g, let's call it fg of x12 and h of x22. They don't have to be always the same function, but each element you choose from some PDF. Okay, so independently. So that's why their joint distribution is a product of the individual distributions. Okay, so this general class of matrices are called Wigner matrices. So let me just give you one example of that. So this is the so imagine that you have a graph with nodes, like, I don't know, again, let's take a 3 by 3 example. So you can construct and then you put a link. So let's say I put a link like this. Okay. So for this graph, I can construct an adjacency matrix. So what is the adjacency matrix? It just says that this will be a 3 by 3 matrix. So it's a number of nodes, whatever number of nodes in your graph. So n by n in general. So this is a 3 by 3. And you put the diagonal elements you put to be 0. So this is 1, 2, 3, 1, 2, 3. And off diagonal elements, if there is a link, you put a +1. Okay, so 1 and 2 have a link, so you put a +1. And 1 and 3 have no link, so you put a 0. 2 and 1, of course, has the same link, so it's a symmetric matrix. And 2 and 3 have a link, so it's 1. And then 3 and 1, no link. 3 and 2 is 1. Okay. So this is called the adjacency matrix of any graph. Okay. And which is all, at least for undirected graph, this is always real symmetric matrix. Okay. So now this famous problem of graph, which is called the Erdős-Renyi graph. So this is a random graph, and the simplest rule, you can have many other different rules, but simplest rule is that you sort of say assign a randomness. You just say that, okay, link is present with probability p and is absent with probability 1 minus p. P is a number between 0 and 1. Okay, so it's either there or not there. Okay, so that means, this element here, for example, this link, it can be either 1 if it is there or 0 if it is not there. So we have assigned by randomness to the graph, which induces a randomness to the adjacency matrix. So now the off-diagonal elements of this matrix for I not equal to j. So this is either 1 with probability p, if that link ij is present, and 0 with probability 1 minus p. Okay, so independent, right? Because this is the Erdős-Rényi, each link is independent. And the diagonal element, of course, remains 0. Okay, so we have a random matrix, random adjacency matrix now, which is real symmetric, whose diagonal elements are always 0, and whose off-diagonal elements are independent of each other, and the probability distribution of these off-diagonal elements, you know, the P of A for I not equal to j. So it's a bimodal distribution. So it's either 1 with probability P. Okay, let's call it little a. Little a is just the element, okay? So it's with probability P it's 1, or with probability 1 minus P it's 0. Okay? And the diagonal element is always 0. Okay? So you see in this notation here, so the f is just a delta function, it's just a deterministic, it's always 0. And the g and h, okay, in this case they are all equal, and they are taken from this bimodal distribution. Okay? So these are called Wigner matrices. So this is a class of, you know, class of matrices that you can generate by just choosing the matrix elements independently from some given distribution. Okay. Now there is a second class of matrices. Okay, I'll just remove this now. So this is Wigner matrices. And the second class, so these are called rotationally invariant matrices, ensembles. So these are these two ensembles, Wigner ensemble and the rotationally invariant ensemble. What does it mean, rotationally invariant ensemble? This is naturally comes again in the context of nuclear physics that I discussed, that, you know, imagine that you are describing your nuclear spectrum, then, you know, it should not depend on which basis you are looking at in your Hamiltonian, right? So you can make a change of basis, then the, you know, probability distribution should be invariant under this change of basis. Okay? So this means that now we have already seen that the volume element does not change under the similarity transformation. So therefore, what I mean, probability distribution means that you have this P of x. You know, I just use the shorthand notations for these matrix elements. P of x dx. This is your probability distribution. So this should be invariant under a similarity transformation. Okay, so these are the rotational invariant matrices. Now we have seen that already this volume element does not change under the similarity transformation. Okay, so this part is already invariant. We have seen that already. So all I need to ensure is that this P of x, this function of the matrix elements, this distribution function, so this guy therefore should be the same as same function P, same function. So you just make a rotation. This function should not change under this rotation, right? Because the volume element doesn't change. So if I want to make the probability distribution fully invariant, so I have to ensure that this P does not change. Okay, so let's take an example. So for example, I mean, I could choose this P of x for the real symmetric matrix, let's say, something like this. So trace of x square. Okay. So trace of x square means, you just take these two matrices, square it, and then take the trace, right? So this for 2 by 2, this will be x11 square plus x22 square plus 2 x12 square. Okay, so just Gaussian basically. Okay, but with these two here, so that it's written in trace. So you see that if I write it in this way, then clearly if I make this orthogonal transformation, trace is invariant, right? Trace of s dagger x square s is exactly same as trace of x square. Okay, so this one doesn't change under the orthogonal transformation. Okay, so so therefore, this is a good rotational invariant ensemble, but I could choose something else. I could, for example, choose any function of trace. So I could choose trace x square, let's say with some coefficient here, trace of x fourth, for instance. Okay. So this one again is invariant under the rotations. In fact, in general, I mean, you could choose any polynomial function of let's say any polynomial function of Vx, okay, ax square plus bx4. So where this is Vx is some ax square plus bx cube plus cx4, etc. Okay. So all this is invariant under this similarity transformation. Okay. So in fact, I mean, when people study matrix models in high energy physics, I mean in string theory and so on, these are exactly called, this is called the matrix potential. Okay, so this is the weight that you choose. Simplest is the Gaussian, which is just a trace x square, but you can have more complicated elements, more complicated potential, matrix potential, which is could be in general polynomial potential. Okay. Okay, so we have these two. Sorry. Yeah, I mean, I'm not writing, the normalization constants here. Okay. Okay. Yes. Yeah, absolutely. I mean, just to give you one example, maybe I'll try to just. So, for instance, another example is what is called the Cauchy ensemble. So, for instance, I could choose P of x to be proportional to, let's say, 1 over determinant of I plus x transpose x to the power some gamma with gamma positive. So I could choose that also. You see that again, if I make a similarity transformation, this guy doesn't change. Okay, so this is like a prefactor, so it's called the Cauchy ensemble. So you can have all possible choices such that the function is invariant under the rotation. Okay. Okay, so now, all right. So now comes an interesting fact. So I've defined the two classes of matrices, right? Wigner matrices and the rotational invariant ensembles. Okay, so you can actually, so imagine that this is a space of all possible matrices with real spectrum. Random matrices. And so there is this class here, which is the Wigner matrices, where the elements are independent. Okay, and there is a class here, which are these rotationally invariant ensembles. And so you see, one example is Gaussian, this particular case. As I said, you know, this you can, up to the normalization constant, you can write this as half x11 square plus x22 square plus 2 x12 square, right? So you can think of this also as a Wigner matrix that is the independent element. So I'm choosing this x11, x12 and x22 independent Gaussian. So therefore their joint distribution is the product of the thing, but except that I'm choosing the variance of this x12 to be half of the variance of x11 and x22, so that this particular combination can be written as trace of x square and is invariant. Okay, so Gaussian distribution. So if I take Wigner matrices with Gaussian distribution and if I choose the variance properly, then I can make it rotationally invariant. Okay, so Gaussian is one example which we can think of belonging to both Wigner as well as rotational invariant ensembles. Okay, but obviously this will not be true if you take, for example, something like trace of x4. So if you take trace of x4, I mean, you see, you cannot write down this as a product of independent distributions. Okay, because x4 will be some complicated function of these elements, right? So Gaussian in one example, which belongs to this, you know, common area between Wigner and rotational. It's both Wigner as well as rotational invariant ensemble. Okay, but now comes an interesting theorem due to Porter and Rosenwig. Get this spelling correct. Which says that the Gaussian is the only one. There is no other distribution you can think of which is Wigner, which is independent as well as rotational invariant. Okay, so Gaussian is the only one. The proof of this theorem is not that difficult, but I will not do it here. Okay, so Gaussian actually plays a very special role because of Gaussian matrices. So these are called Gaussian ensembles when you choose the weight like this, trace of x square. So if it is a real symmetric matrix, so this is called Gaussian ensemble. So if it is a real symmetric matrix, then this is invariant under a orthogonal rotation, right? Because in a real symmetric matrix, you have to, on the transformation that diagonalizes it, it's an orthogonal transformation. So these are called the Gaussian orthogonal ensemble. So GOE, you have seen these terms before, Gaussian orthogonal ensemble. If it is a complex Hermitian matrix, then this is invariant. So the similarity transformation there for complex Hermitian is the unitary matrix, right? So the S that I wrote down there, S transpose S, is identity for real symmetric matrix. But for if you take a complex Hermitian matrix, you have to take a unitary matrix, and this unitary under which it's invariant. So this is the this is what is called. So this in that case, this will be trace, again trace of x dagger x. Okay, so because x is complex, so in that case it will be half trace of x square, but which is you can think of as x dagger x. X dagger is same as x because it's Hermitian, so trace of x square, but it's invariant under unitary transformation, and that's why it's called the Gaussian unitary ensemble, GUE. And the third one, which I did not discuss, which is the quaternion case, self-dual. Which are invariant under what is called the symplectic transformation, and which is sort of analog of this the unitary and orthogonal transformation, and this is called the Gaussian symplectic ensemble. Okay, so Gaussian matrices sort of play a very special role also we'll see later when we come to cold atoms. But a special role because of this fact that this is the Wigner and both Wigner as well as rotational invariant ensemble. Okay. So now, what are the advantages of these ensembles? So this is like the choice of ensembles that we use in statistical mechanics. You know, the canonical and microcanonical, grand canonical, etc., etc. So depending on which problem you are looking at, so again, so this is these two classes, okay. So Wigner. So what are the, so this is, let me call 1 and this is 2. So 1. So these matrices are, you know, the advantages are that they are, okay. So this is Wigner and this is rotationally invariant. Yeah? Wigner means that you choose the independent entries. You choose the entries independently. Yeah. Okay. So what are the advantages of Wigner matrices? So number one is that it's numerically easy to generate. Now imagine that you are to generate your ensemble numerically. So all you have to do is to just, you know, take the matrix elements and choose them independently from some distribution. Okay. So it's very easy. Whereas, you know, here numerically often it's hard, except for the Gaussian. Okay. For instance, except okay, so for instance, I mean, if I choose this P of x, suppose I want to generate P of x rotational invariant ensemble with which is okay up to some normalization constant exponential minus half, let's say trace of x square minus b trace of x fourth. So suppose you want to study this matrix numerically. Okay, how will you generate this? So you see the joint distribution of the entries, therefore, is this. So if you write in terms of the matrix elements, so this will be, you know, summation xij square, all ij, this is this part, and then this guy here will be xij or lots of indices, xjk, xkl, xli, sum over all ijkl. Okay, so you want to generate some random numbers, you know, n into n by 2 random numbers from this distribution. So it's not so easy because they are horribly correlated. Okay. So the moment you put this term, extra term, the xij's, their distributions get completely correlated. Okay. So the entries are themselves very strongly correlated, and so you cannot, you know, it's not so easy to generate this numerically. Okay. So this is one point. Now for this, in contrast, it's very hard to, so as I told you, the main problem is that once you assign this joint distribution of the entries, okay, after that you want to compute the distribution of the eigenvalues, right? Now for Wigner matrices, it's extremely hard to compute the joint distribution of eigenvalues. So for instance, I will give you an example, which is the adjacency matrix of the Erdos-Renyi graph. Nobody knows what is the joint distribution of the eigenvalues. Okay, it's still an open problem completely. Okay, but for rotational invariant ensemble, the advantage is that we can calculate, and this is what I'll do in the next lecture, the joint distribution of eigenvalues. So if you tell me what is this P of X and the fact that it's rotational invariant, I'll be able to tell you what is exactly the joint distribution of eigenvalues. Whereas for Wigner matrices, I cannot do that in general. Okay. There is one exception here for Wigner matrices, which is called the beta ensemble. This is by very non-trivial result by Dimitriou and Edelman. So this is a particular ensemble which is a tridiagonal matrix with different distributions for different elements. Maybe I'll discuss that later in a little bit detail. And you choose this from a chi-square distribution, and for that case, they were somehow managed to calculate the joint distribution of eigenvalues. But in general, this is very hard. Okay, and but we'll see in the next lecture that for the case of rotational invariant ensemble, somehow it's very easy to compute the joint distribution of easy. I mean, it's sort of relatively easy to compute the joint distribution of eigenvalues, and you can do that explicitly because there is a separation between eigenvalues and eigenvectors, which happens because of the rotational invariant property that we'll see in more detail in the next lecture. And so okay, so what I just to summarize, basically, so what we have done today is in the first half, I just give an introduction of the RMT, and I told you that it originally appeared in the statistics literature, and then how Wigner used it in nuclear physics, and why it is still important, and why there are so many applications. I talked about quantum chaos. I talked briefly about zeta function, but you will hear from Giuseppe's talk more later. And in the second half, I just introduced the basic how to choose a random matrix ensemble. Okay, and so in some sense, there are two problems in random matrix theory. So one is that given the joint distribution of entries, calculate the joint distribution of the eigenvalues. So this is a first problem, and the second problem is that imagine that you can calculate this joint distribution of eigenvalues, but the story is not yet over, because I can give you this formally, but then you want to calculate some observable, for example, spacing distribution or the distribution of the largest eigenvalue, many other observable, and that's not always easy. I mean, even if I give you explicitly, it's like the Ising model. Everybody knows what is the distribution of the energy of a different configuration the Ising model is, 3D Ising model, let's say. Okay, but still to calculate, for example, magnetization or any other correlation functions are extremely hard. And same thing here. So there are two steps. So one is to first get the statistics of the eigenvalues, joint distribution. That itself is very hard. As I said, for Wigner matrices in general, you don't know how to do it. And the second step is that, but for rotational invariant ensemble, we can do it. And then, given this joint distribution, calculate observable. And this is the domain of statistical mechanics. Okay, calculate observable. So this part, if you like, is a sort of matrices, random matrix. But once you calculate this, you can forget about the matrix where it came from. You can think of as a gas of particles, with positions lambda 1, lambda 2, lambda 3, lambda n. And you are given the energy of a given configuration, and you want to calculate certain observables. So this is RMT, if you like, and this is statistical mechanics. Okay. So what I'll do in the next lecture is to show you how we can calculate the joint distribution for rotational invariant ensemble, and then we'll talk about different observables and so on. Okay, I think I'll stop there. Thank you.